I hope you have memorized all the kinematics equations you have learned so far. If not, you may wish to pause this video and memorize them now. We're going to use those equations to solve more problems. This one is a two-part problem. A car is traveling at 22 meters per second when its driver sees a deer in the middle of the road in the front. It takes him 0.7 seconds to actually step on the brakes, after which the car decelerates at the rate of 8 meters per second squared to a stop. How far does the car travel before coming to a stop? We'll assume that the car travels at a constant velocity before the brakes are stepped on. This is a two-part problem because there are two kinds of motion involved. Before the brakes are actually stepped on, the car travels at a constant velocity. After the brakes are actually stepped on, the car travels at a constant acceleration. So we have to take care of one part at a time. Now the reason why you have a 0.7 seconds over there is because when the driver decides to stop the car, the brain sends a signal, and the signal goes down the spinal cord, tells the muscles to lift the legs, and then the brakes are actually stepped on. It takes time for that signal to process. The more alert you are, the shorter the reaction time. That's what we call that time. But no matter how alert you are, your reaction time is never going to be zero. Okay, so let's see. The first part, you have constant velocity motion. If it's constant velocity motion, it's simple. There's only one equation you will need. That is the displacement is the velocity times time. So all you have to do is to multiply the velocity by the time. For the first part, the constant velocity motion, the car was traveling at 22 meters per second, and it lasts 0.7 seconds. So it's 22 times 0.7. The distance traveled will be 15.4 meters. Then the second part, you would have constant acceleration motion or the deceleration. Okay, the problem tells you the deceleration is 8 meters per second, so we will say this is -8. For constant acceleration motion, we need to know three things. So there are two other things we know. Do we know about the 22 meters per second? Yes, that 22 meters per second will be the velocity for the first part. The entire first part is the same 22 meters per second. And then the second part, that means the initial velocity at the second part is still 22 meters per second. Now, can we say the time is 0.7 seconds? No, we can't do that because that's just the time duration for the first part. The second part, the time, is whatever it takes for the car to stop. So we don't know the time. The time is not 0.7 seconds. So what is the third thing we know? We know that the car has to come to a stop in the end. So that means we know the final velocity is 0. And what we want is the displacement, delta x. So we know three things. We're looking for the fourth one. There is no time involved. That means the equation that does not involve time can be convenient. Do you remember that equation? That's v squared equals to VO squared plus 2a times the displacement. So the final velocity is 0, initial velocity 22, the acceleration -8, and we don't know the displacement. So this will be 0 equals to 484 minus 16 delta x. I can move the 16 delta x to this side. So if I divide by 16 on both sides, I can find the delta x, which gives me 30.25 meters. So the distance traveled for the first part is that. Second part is this. That means the total stopping distance would equal to 15.4 plus 30.25, which gives you 45.67 meters. That is the total stopping distance. Now, in case if you're interested in using a velocity versus time graph to solve the problem, you can certainly do that. The car at first goes at a constant velocity. The velocity is a constant 22 meters per second, and that lasts 0.7 seconds. And then the car slows at a constant rate. The acceleration is the slope of the graph. If your acceleration is a constant negative number, that means you have a constant negative slope, so the graph goes down this way. And then if you want the displacement, you just need the area under the graph. And this entire area will give you the total stopping distance. Now this one is a proportion problem. A Corvette can accelerate at 2.5 times the rate of a Prius. Now both cars accelerate from rest at their maximum acceleration, and we're pretending that they accelerate at constant rates. Now part A, if it takes time t0 for a Corvette to reach 60 miles per hour, how long in terms of t0 does it take for a Prius to reach the same speed? Part B, if it takes a Corvette a distance d0 to reach 60 miles per hour, how far in terms of d0 does it take a Prius to reach the same speed? Part C, how far in terms of d0 does it take the Corvette to reach 30 miles per hour? In part A, both cars have to reach the same final velocity. They have different accelerations, so we want to see how the time depends on their acceleration. Now, if you look at the constant acceleration motion equations, which one it will be the most convenient to use if you want to relate acceleration and time, and you know the final velocity is the same? So this one will be convenient. So that's what we're going to use. So we have V equals to VO plus AT. Of course, the initial velocity is 0 for both cars. And that means you can solve for t because we're looking for time. So if we solve for time, then it is v final velocity divided by the acceleration. The final velocity is the same for both vehicles. So this means time is proportional to 1 over acceleration. And the acceleration for the Prius changes by a factor of 1 over 2.5 because the Corvette's acceleration is 2.5 times that of Prius. So Prius's acceleration is 1 over 2.5 times the Corvette's acceleration. So the acceleration changes by a factor of 1 over 2.5. So this gives me 2.5 times. That means the time changes by a factor of 2.5. The original time for the Corvette is TO. So you just have to multiply the O value by the factor by which it changes. So 2.5 TO is the answer. Now in part B, both cars will reach the same final velocity. And the two cars, they have different accelerations, and we want to know how the different accelerations would affect the displacement. So let's look at the equations again. We want to relate the acceleration and the displacement when we know they reach the same final velocities. Of course, they also start with the same initial velocity. So this equation is convenient. So we have v squared equals to VO squared plus 2a delta x. The initial velocity is 0 for both. And we want to find the displacement, so we can solve for the displacement. So displacement would be v squared divided by 2a. Now the v squared is a constant, 2 is a constant. So when you use the proportion, you can leave them out. So the delta x is proportional to 1 over a. Again, the acceleration of the Prius is 1 over 2.5, which is the same as there. That's 2.5 times. the original displacement for the Corvette is dO. Now it changes by a factor of 2.5, so your answer would be 2.5 times the dO, and that would be the distance for the Prius. Now for part C, we're looking at the Corvette and the Corvette. That means the same car, same acceleration, but the final velocity this time is the different one. And we want to see how the different final velocities will affect the distance. This time, same acceleration, and we want to relate the final velocity and the distance. So, same equation. V squared is VO squared plus 2A delta x. Again, the initial velocity is 0, and we want the displacement. So displacement again is V squared over 2A, but this time the 2 is the one that's the same. The acceleration is the same, but the final velocity changes by a factor of 1/2. So we have to plug in the 1/2, or kind of, it's not really plug in, but we're going to use 1/2 for V and then square it. This gives me 1/4. So the displacement changes by a factor of 1/4. The displacement used to be dO, now it is 1/4 times the dO. If you're looking for more problems to practice, you may wish to go to my website and download my practice problems with fully worked out solutions. You can find the web address in the description of this video. I will see you next time.